Hi, in this video, we want to take a look at estimating using data. All right, so our game plan is that we are interested in knowing a true value. So let's say I want to know the true average height of Americans in the United States. Now, there is no way to actually know what is the true height of Americans in the United States. Now, what I can do, though, is I can estimate it using data. And so we're going to talk about that estimation process. Now, this is chapter 6 from Essential Biostatistics, which is a Cengage textbook by Bernard Rosner. And we're going to run through the PowerPoint slides. All right, so we want to infer the properties of an underlying distribution in a data set. This inference is usually based on inductive reasoning rather than deductive reasoning. That is, we're determining a best fits model among different probability models. All right, so there's two types of statistical inference that we'll talk about. We're going to talk about first one, estimation, second, hypothesis testing. So in estimations, really we're trying to get our best guess possible off of this. So estimation concerns with estimating the value of a specific population parameter. These specific values are referred to as point estimates. Sometimes interval estimation is carried out to specify a range within which the parameter values are likely to fall. So in estimation, I'm giving my best guess. When you hear point estimate, that is our best guess of what the value is. Now, hypothesis testing, this is concerned with testing whether the value of a population parameter is equal to some particular specified value, or greater than or less than. All right, so now the relationship between population and sample. A random sample, a selection of some members of the population such that each member is independently chosen and has a known non-zero probability of being selected. Simple random sample, each group member has the same probability of being selected. So there's, for reference, target, or study population, the group we want to study, the random sample is selected from the study population. Random sampling is not the only one used in practice. A population alternative is cluster sampling. An alternative method to selecting the sample is to have a computer generate a random set of random numbers. All right, so there's different types of sampling that we can go through. So there's random sample. So the idea is that we are going to truly randomly select what we want. And that's, when you think of that, usually you're thinking of simple random sample of randomly selecting each one. We could also do cluster sampling, where here the idea is that we're going to randomly select a location or a subgroup and then try to grab all the information we can within that subgroup. And there's tons and tons of variations on this. There's every field that uses statistics uses slightly different terms for this. Really, what we want to do, we want to have our true goal is to have our sample data reflect the population of interest as much as possible. We don't want to have things skewed in one way or another. All right, now random number tables. So a random number, or a random digit, is a random variable x that takes on the values 0 through 9, or here they're saying 1 through 9 on this one, with equal probability. Thus, the probability of 0, probability of 1, probability of 9, so on, are all 1 over 10. A computer-generated random number are collections of digits that satisfy the following two properties. Each digit, 1 through 9, is equally likely to occur. Should be 0. The value of each particular digit is independent of the value of any other digit selected. Computer programs are sometimes used to generate large sequences of random digits. These numbers are sometimes referred to as pseudo-random numbers because they are simulated to approximately satisfy the above two properties. All right, so 100% correct speaking, your computer is more than likely not generating truly random numbers when you're doing random number generation. And there is a difference. Operationally, most of the time it doesn't matter, but if you want to be super, super precise, your computer is probably generating pseudo-random. It's not quite random. It looks really, really close to random, but not quite. So just be mindful of that in your research, in your work, that when you could say you're using a random number generator and somebody may go, whoa, 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 it's not 100% random, which is true, but operationally doesn't make a difference. All right, so the process of random selection. Let's say each of 1,000 participants are assigned a number from 0 to 999. 20 groups of 3 digits are selected, starting at any position in the random number table. And then we do random assignment. This differs from random selection in that the number is fixed in advance. In a finite sample, random assignment works better than random selection because it ensures all equal number of patients assigned to each group. All right, so this random assignment aspect, this is in the situation where, let's say I have 50 possible people to work with, and that 50 is everything I have, and I'm not in a situation where I could potentially sample from the true large big population. So consider the difference between I'm interested in studying studying Americans, so any American in the United States is possible for the study, or the situation where I have 50 subjects and I need to work with these 50. Well, random sampling will work. Can work very well when I have the larger group to sample from, but there can be a few glitches with the smaller sample size, the smaller numbers, and what's going on. And in that case, we'll use random assignment. And so here are some tables to show us how we would go through and work through this. The main tab has a function that allows sampling from the columns. The user must specify the number of rows to be sampled. One limitation in obtaining random samples this way is that the default option is sampling without replacements, whereby the same data point from the population cannot be selected more than once in a specific sample. That is, repetitions are not permissible. All right, so that is an important aspect of anytime that you're doing random number generation, random sampling simulations, is do we have with replacement or not? Okay, imagine the situation that we're going to go through and I'm going to pick names out of a hat for a prize. Let's say that we've got 2 prizes. We have first one's a car, second one is a vacation to Hawaii. 2 prizes. First situation, I pull out a name, I call it, I put it back in, I shake it up, I pull out another name. Since I put it back in, there's an opportunity for them to get 2 prizes. So one person could really, really luck out. In that case, that's sampling with replacement because I put it back in with replacement. Now, the other situation, once again, we have 2 prizes. One is a car, second one is a trip to Hawaii. I pull out a name, I look at it, I call it, I put it to the side. That name can never be called again for a prize. I pull out another name. I look at it, I call it out. In that second one, that's sampling without replacement. So in the first situation, potentially the same person could get both prizes. And a lot of people will be angry and claiming that's rigged. In the second situation, the person can only get 1 prize. So imagine the situation where we have a gift card, a $5 gift card to Starbucks, a $10 gift card to Target. Then we have a trip to Hawaii. You're not going to want the first 2 prizes. So if it's sampling without replacement and your name gets called on the first or second, you're going to be angry. You're going to be frustrated because you lost the chance to go to Hawaii because you got that $5 gift card to Starbucks. So sampling with replacement will have a huge impact on our results. Sometimes it doesn't even make sense to sample with replacement. So just make sure you know which settings you've got your computer on when you do this. All right, randomized clinical trials. Randomized clinical trials is now accepted as the optimal study design in clinical research. A randomized clinical trial is a type of research design used for comparing different treatments in which patients are assigned to a particular treatment by some random mechanism. The process of assigning treatments to a patient is called randomization. Randomization means the type of patients assigned to different treatment modalities will be similar if the sample sizes are large. However, if sample sizes are small, then patient characteristics of treatment groups may not be comparable. All right, so imagine a situation where I only have, let's say, 4 people. Let's say 3 are male, 1 is female. Well, if I break that up into 2 groups, I'm going to have a group of all males. So things will not always be comparable if I have a small sample size. It is customary to present a table of characteristics of different treatment groups in randomized control trials to check that randomization process is working well. All right, so here we have different groups. And so what we're trying to do here is just make sure that we have an even number. All of my subgroups are evenly dispersed across all of the groups. So here we have, age groups. You'll notice that this adds up to 100, this adds up to 100, this adds up to 100, and we want these percentages to be relatively close. Now, with smaller sample sizes, or we have very, strong correspondence between subgroups of different types. So like, let's say if I have like age and race could be like, corresponding well within my particular group of people. In that case, it'll be harder to make things even across all the groups. So, I want these percentages to all be relatively close to each other as I go across. So here is race. So here we can see that we have race and sex together. Here we have education. Here we have, the average blood pressure. And so what we want here, so these are about the percentage of the variable throughout. Here's the average of the numeric variable, and we want these to be close to each other. Antihypertensive medication percentage, we want it to be close across the 3 groups. Then smoking status, once again, we want to be close. We want to see everything's relatively even when we work this out. And we would want our totals and all of these values to be close to the overall population known. So if I knew like what percent of the US population never smoked, how many were past smokers and current smokers, I would want all the values in all these columns to be close to the true overall population values. All right, so here's baseline characteristics of randomized SHEP participants by treatment group. And so I've got my active treatment group, my placebo group, and then the overall. All right, so in this, my office has an automatic light turner offer to save energy, and I can't quite wave to get going. All right, so now here we have, our active treatment group, our placebo group. We want these to be close, and we want, all 3 of these to be close to what the history of myocardial infarction is for the study population that we actually want to know about. And so looking to see that these are close. So things are looking pretty good to me. Usually when I have a larger sample size, then it'll be easier to get the percentages or the values to be evenly distributed. All right, design features of randomized clinical trials. Methods of randomization. So there's random selection, random assignments, etc. In clinical trials, random assignment is sometimes called block randomization. That's the term I learned when I was an undergrad. A block size of 2n is predetermined, where each of the 2n patients entering the study, n of the patients are randomly assigned to treatment A, and n of the patients are assigned to treatment B. So we're keeping sample size even. For more than 2 treatment groups, if there are k treatment groups, then a block size must be kn, where every kn patients, n patients are randomly assigned to the first, and then n are assigned to the second treatment group, and so on until you have everyone assigned to a group. Now, stratification, this is another technique. Now, this is also used in the randomization process. So here, what we're going to do, we're going to divide our patients into subgroups, and we're dividing the subgroups by some feature that we, before the study, believe is very important. And then we're going to make sure that things are relatively evenly distributed in this manner. So stratification, I'm identifying something that's important, and then I'm breaking up my patients, the subjects in my study by that particular feature. So we'll do separate randomization lists are maintained for each stratum to ensure comparable populations for each stratum. This is called stratification. Each random selection, such as ordinary randomization or random assignment, block randomization, might be useful for each stratum. Typical characteristics used to define strata are age, sex, or overall clinical condition of the patient. In blinding, we use this to make sure that there's less opportunity for bias in our results. A clinical trial is called double blind if neither the physician nor the patient knows what treatment he or she is getting. A clinical trial is called single blind if the patient is blind as to the treatment assignment, but the physician is not. A clinical trial is unblinded if both physician and patient are aware of the treatment assignment. The current gold standard in clinical research is the randomization double-blind study in which patients are assigned to treatments at random and neither the patient nor the physician is aware of the treatment assignment. This prevents biased reporting of outcomes. However, it may not always be feasible in research settings. In some cases, a treatment progresses. As treatment progresses, the side effects may strongly indicate actual treatment received. All right, so imagine a situation that we randomly assign patients to different treatments, and then we don't tell the doctors which treatment they're giving each patient. So there's treatment A, treatment B. Doctor doesn't know, patient doesn't know. That is double blind. Now, as things progress, as things turn out, it might be that treatment A has a side effect that treatment B does not have. If we see that side effect, then that physician will know more than likely that that patient is receiving treatment A. And so there, that can destroy the double-blind aspect of the study. Now, for estimation of the mean of the distribution, a natural estimator to use for estimating the population mean, mu, is the sample mean. By far, the most common way to go, the benchmark way, is just to take the arithmetic average. X bar is a single realization of a random variable over all possible sample size n that could have been selected from the population. X denotes a random variable. So this is capital X denotes a random variable, and little x denotes a specific value of that random variable. The sampling distribution of x bar is the distribution of values of little x bar over all possible sample size n that could have been selected from the reference population. All right, so here is a frequency distribution of the sample mean from 200 randomly selected samples of size 10. The expected value of x bar over its sampling distribution is equal to mu. All right, so what this is saying here is that the population average of the sample average is equal to the population average of the data that we are collecting from. So mu here is the true population average of the data we're taking numbers from. Now, we don't actually know what mu is. We're trying to estimate it. It works out that if I take the sample average, then the expected value of that sample average will be equal to the population average of the data we're selected. It will be an improvement on our estimate over the regular data that we have. So let x1, x2, x3, x4, xn be random sample drawn from some population with mean mu. Then the sample mean of x, expected value of the sample average, is equal to the population average regardless of the underlying distribution of the data. X bar is regarded as an unbiased estimator of the population average. An estimator of parameter theta is referred to as theta hat. All right, so in statistics, we use Greek letters to represent the unknown values that we are attempting to estimate. And so this is what I would like to know, but I don't actually know it. I'm using data to get my best guess. When I put a hat on it, this hat indicates that this is my estimate of this value. So an estimator, theta hat, of the parameter theta is an unbiased estimator if its expected value is equal to the value we are trying to estimate. All right, what does that say? It works out that I can have my best guess, my best estimate of a value could be biased. Now, it could be high or it could be low, but when I'm making my best guess, I don't know which way it would be going. I don't know if it's high or it's low. Practically speaking, most of the time, our best guess is a little bit off, but it is our best guess, and it's usually pretty close. This unbiased is just saying that on average, my best guess will be equal to the value I'm estimating if I have an unbiased estimator. So the average value of theta hat will be equal to the value I'm attempting to estimate with a large number of observations if I have an unbiased estimator. Now, for symmetric distributions, many unbiased estimators exist, including the sample median and the average value of the largest and smallest data points in the sample. X is usually chosen over other unbiased, so X bar, this should be X bar, is usually chosen over other unbiased estimators because if the underlying distribution is normal, then it can be shown that the unbiased estimator with the smallest variance is given by X bar. This should be X bar. Thus, X bar is called the minimum variance unbiased estimator. All right, this is a big deal in statistics. Minimum variance unbiased estimator. Unbiased means that the average best guess value my best guess value on average is going to be spot on average. Minimum variance means that things are going to be spread out less over that. So if I was to go through and repeatedly collect data and get my best guess, my point estimate, the unbiased estimator tells me that on average, it's where it's supposed to be. Now, remember, when we do things, when we deal with data, we have to worry about its location on the number line and how spread out it is. Unbiased estimator says the location is where it should be, central tendency, Minimum variance says that it's spread out as little as possible of all possible estimators. And so here we have sampling distributions of several estimators of mu for 200 random samples of size 10 selected from the population of 1,000 birth weights given in this table. Sampling distribution of the sample mean, sampling distribution of the sample median, and here the sampling distribution of the average of the largest and smallest observations. So here we can see that this is, compared to the others, pretty tight. We can see that this is the most spread out of all of these. Now, on average, X bar, the median, and average of the two extreme values, on average, are going to be centered on where we want them to be. But you can see that this one is more spread out than the others. This one's going to have the least variance because you can see everything's clustered more towards that center. Therefore, this is the least variance one that we could possibly get. All right, so let x1, x2, x3, all the way xn be a random sample from a population with underlying mean mu and variance sigma squared. The set of sample means in repeated random sampling of size n from the population will have a variance of sigma squared divided by n. All right, so if I take data that has variance sigma squared, the sample average will have a variance of sigma squared divided by n. So variance is my measurement of spread. Well, here you can see I'm dividing by n. So if I had a sample size of 10, I've decreased the variance to 1/10 of what it was for the original data. So this is a huge decrease in variance. The standard deviation of this set of sample means is thus the square root of the variance and is referred to the standard error. So when you see standard error, that's going to be the standard deviation of an estimate. A reasonable estimator of the population variance, sigma squared, is the sample variance, S squared. Remember that this is the average of the square of the difference between the value and X bar. The standard error of the mean, abbreviated SEM, or the standard error SE, usually I see it as SE in my work, is given by sigma divided by square root n, and is estimated by S divided by square root n. The standard error represents the estimated standard deviation obtained from a set of sample means from repeated samples of size n from a population with underlying variance sigma squared. All right, now here's an illustration of standard error for this. All right, so here, sample size of 1, sample size of 10, sample size of 30. See how spread out this is? See how spread out this is, and see how spread out this is. And you can see that all of these random samples have a central tendency pretty close to each other. Now, there's a little bit of deviation. They're not exactly lining up perfectly. They are random. Things are not, when we're dealing with random data, it's not going to behave exactly like the theory says it should, but it'll be close. We see that this is more spread out than this one, and we see that this one is even less spread out than this one. As the sample size increases, my data is going to get, my sample averages are going to get closer and closer to the true population average. Now, standard error is not the standard deviation of an individual observation, rather that of the sample mean. It is a quantitative measure of the variability of sample means obtained from repeated samples of size n drawn from the sample population. All right, so it is directly proportional to both 1 over the square root of n and the population standard deviation, sigma, of individual observations. So it's proportional to 1 over the square root of sample size, and it's proportional to the standard deviation of the population we are sampling. Precision of the estimate of mu is affected by the underlying variance, sigma squared, from the population of individual observations and the sample size. Sigma squared can sometimes be affected by the experimental technique. So if I mess up something in my sampling, I might be sampling something other than what I actually think I'm working on. Central limit theorem. All right, this is a big one in statistics. Let x1, x2, x3, x4, all the way up to xn be a random sample from some population with mean mu and variance sigma squared. Then for large n, x bar, the sample average, is a normal random variable with population average mean mu and variance sigma squared divided by n, even if the underlying distribution of the individual observations in the population is not normal. The tilde is used to represent approximately distributed. All right, so here, what this is saying is that this data can, as long as it's numeric, it can be any population of data as long as it has the same mean and variance, independent, identically distributed. Then the sample average, no matter how I got the data, as long as it has independent, identically distributed, mean mu, variance, sigma squared, then the sample average is going to be normally distributed. That's the first takeaway. We know it's distribution. Then we know the population average. Then we know the variance. I mean, that's a lot to take in. That is a lot. This is a big deal. All right, in mathematics, if you see theorem and you see a name, you know it's a big deal. Central limit theorem is a big deal. This theorem allows us to perform statistical inference based on the approximate normality of the sample mean, despite the non-normality of the distribution of the individual observations. So why is this a big deal? Because no matter how I got my data, as long as it's independently and identically distributed data, mean mu, variance sigma squared, then I know I have the distribution. I know the shape, I know the mean, I know the variance. I can reach statistical conclusions without knowing much about the original data source. The skewness of the distribution can be reduced by transforming the data using log scale. The central limit theorem can then be applied for smaller sizes than if the data are retained on the original scale. So it works out that this approximation aspect works better if our data, the original data's distribution, looks like the bell curve. If it looks like the bell curve, then the approximation is even better. What this log scale stuff at the bottom is saying is that if I have highly skewed right data, I could take a logarithm of my data and boom, it looks more like a bell curve. Therefore, I can make an inference with less data, better approximation. And so here we can see, here are some averages. N equals 1, N equals 5, N equals 10. And you can see that the larger the N, the more it looks like the classic bell curve. All right, now let's talk about estimation intervals. All right, so interval estimation, this specifies a range within parameter values are likely to fall. If we re-express x in a standard form by z equal to this funny looking fraction, x bar minus mu over sigma divided by square root n, z should follow a standard normal distribution. Hence, 95% of the z values will be between negative 1.96 and positive 1.96, because these values correspond to the 2.5 and 7.5 percentiles of standard normal. Now, however, this assumption, for this to work, sigma has to be known, which it's rarely known in real life. So where we're going with this is that I have a point estimate. I have a single value best guess. Well, that's the location of my estimate. That doesn't give me an idea of how sharp of an estimate it is. What we're going to do, we're going to expand things to be like, I'm 95% confident that the value that I want to know about is inside this interval. And the width of that interval is going to give us an insight into how good our estimate really is. So let's talk about the t-distribution. With modern machines, if you can, use the t-distribution instead of the normal distribution. Back in the day, back in like the 80s, before people had computers doing statistics for them, what they would do, they would take tables, they would have to look stuff up. It was a long, tedious process. It slowed things down, and that's how they did it because that's the technology that they had to support them. Modern statistics, if you can use the t-distribution, just use the t-distribution instead of the normal distribution. For a lot of cases, it's good enough. There are times when we have to use the normal distribution, but those are usually deeper down the road, later in your statistics career than this course. All right, so sigma can be estimated by the sample standard deviation S, and we can go through and compute this value. Now, there's something to point out. Here, I'm using data to estimate the sample average with X bar. I'm using the data to estimate the standard deviation with S. All right, so I'm estimating twice in this fraction here. Previously in the slide, I've got X bar minus mu sigma over square root n. You notice that the sigma, that is a population value. That in this scenario, that is a known particular value. Here, I don't know what the standard deviation is. I'm estimating it. So I've got another layer of like randomness going on in my statistics. So what we're going to do, instead of using the normal distribution, we're going to use the t-distribution. All right, so back in the day, William Gossett was, according to legend, working for Guinness, and instead of doing his work, he was doing mathematics. And he published his work under the pseudonym Student because he didn't want to get in trouble for publishing when he was, supposed to be doing his work. So the distribution of X bar minus mu divided by S over square root n is referred to as Student's t-distribution. And so something that is important about this is that this distribution depends on our sample size. The t-distribution is not unique, but is a family of distribution indexed by a parameter referring to the degrees of freedom of the distribution. So if x1, x2, x3, xn, all the way, all the values of our sample are all distributed normal with mean mu, variance sigma squared, they're independent, identically distributed, then this fraction of X bar minus mu divided by S divided by square root n is t-distributed with n minus 1 degrees of freedom. All right, so the thing to point out here is that I have two things coming from my sample. I have point estimate and standard deviation estimate. Student's t-distribution is a family of distributions indexed by the degrees of freedom. The t-distribution with d degrees of freedom is referred to as the t sub d distribution. The 100 times youth percentile of a t-distribution with d degrees of freedom is denoted t sub du. So this is where the probability that the t random variable with d degrees of freedom is less than or equal to t du is equal to u. So this is a probability value. And now here, this is trying to show the difference between the t distribution and the normal distribution. All right, so the dark line is the normal distribution. The t distribution with 5 degrees of freedom is the dashed distribution. You'll see that here, it's a little bit lower in the middle, and it's got heavier tails. It's got more data appearing in the tails. What this says is we're expecting to see less data close to 0 and more data spread out, typically. So here's a comparison of the 97.5th percentile of the t-distribution and the normal distribution. And so the big takeaway here is that we expect to see more values farther away from zero when I'm working with a t-distribution than normal. The percentage points of the t-distribution for various degrees of freedom, the youth percentile of a t-distribution with d degrees of freedom is found by reading across the row marked D and reading down the column marked U. Every single statistics platform will do these calculations for you. If you can, don't use tables. Let the machine do the work for you. Now, for a confidence interval, we're going to have a percentile for the mean mu of a normal distribution with unknown variance will be given by this. All right, so this formula, I have X bar, that is my best guess value. And then I'm going to go sum to the right. I'm going to go sum to the left of that. Here I'm subtracting, so I'm going a little bit to the left. Here I'm adding, I'm going a little bit to the right. So what we're going to do, we're going to take an interval of numbers. The middle is my best guess of the population mean. Then I'm going to take, how far left and right do I go? I'm going to take t times standard deviation divided by square root n. I'm going to go plus or minus in both directions. All right, so here, this corresponds to our number of degrees of freedom and how much confidence do I want to have in that percentile. And this reflects how much precision I feel like I'm getting off of my data. For shorthand notation, it's X bar plus or minus T times S divided by square root n. I feel like it's better presented as an interval to be explicit. Confidence intervals for the mean of a normal distribution, so large sample case. It works out that if I have a super big amount of data, that T part in there with the degrees of freedom, I can actually replace T with the normal distribution approximately. And the larger the sample size, the closer my T distribution will be to the normal distribution. If I have a huge number of degrees of freedom, it's usually close enough to the normal distribution that I could just use normal. Now, you'll notice that here, the difference here than in the previous slide, here I have a Z, here I have a T. All right, I have T n minus 1, 1 minus alpha over 2. Here, I have a Z, 1 minus alpha over 2. I've dropped the degrees of freedom aspect and replaced the T with normal distribution. All right, so this is once again an approximation. Now, what I want you to do in real life is if you're doing real life mathematics and you can use the T distribution, let the computer do the calculation for you. Don't worry about the normal or the T aspect. It works out in some types of problems that it's not really clear when we should transition or how to proceed. And sometimes, just to get around other technical details, we'll use the normal distribution. And so this is a reasonable way to go. So this author says the interval should only be used if n is greater than 200. Just let you know, when I was an undergrad, I was told 30. So that's a kind of a big difference, but whatever. Honestly, modern computers, you should be using the T distribution if you can. Some problems you can't. If you can't, use the normal approximation. However, it can also be used with n less than or equal to 200 if the standard deviation is known, replacing S by sigma. But I can tell you in real life, we usually don't know the true sigma because I'm doing research and I'm using data. If you're using data, you don't know what's going on. The boundaries of the interval depend on the sample mean and the sample variance and the level of confidence that you want and which distribution you're going to use. And things will vary from sample to sample. If you go out, collect data, get your interval, go out, collect data again, you're going to have different intervals. They're probably going to overlap substantially, but there could be a difference. All right, so here what this is doing, this diagram is trying to show you how my intervals will change from sample to sample. The idea here is I went out, I collected data several times, So I went, I collected a sample size. Then I went, collected more observations in the second group. Then I collected observations for the third group, collected observations for the fourth, collected observations for the fifth group. All right, so I had 5 different times that I went out and collected data. And when I collected data, I had multiple observations. All right, so in this first one, my point estimate was 1.17, then 132, 117, 107, and then 112. And here we can see this interval width. So the interval width, the wider it is, the less precision I have going on with my estimate. So even though I'm running things the same way and I'm collecting my data, I can see that I don't get exactly the same value every single time. Overall, the collection of 95% confidence intervals that could be constructed from the repeated sampling of size n, if I do this over and over and over, 95% of them will contain the parameter that I actually want. The length of the confidence interval indicates the precision of the point estimate. If it's wider, I have less precision. If it's a narrow interval, I have high precision. So factors affecting the length of a confidence interval. The length of a confidence interval for mu is equal to 2 times t times s divided by square root n. And is determined by, well, n, s, and alpha, because this reflects how much confidence I want in my interval. And as the sample size increases, the length of the interval decreases. As the sample standard deviation, as this increases, the length will also increase. So this is reflecting our the variability of our observations. And alpha, this reflects the level of confidence that we want to have. So as alpha decreases, the length of our confidence interval increases. Usually only n and alpha can be controlled. S is a function of the data that we're studying, and whatever it is what it is. Although S itself can sometimes be decreased if changes in techniques can be taken to improve our sampling, to reduce our measurement error or day-to-day variability and so on. But usually, from a statistician point of view, n and alpha are the two that we have control over, specifically n. Bigger n, usually better result. All right, so the estimation of the variance of a distribution. All right, so point estimation, let all of our x's be a random sample from some population, independent, identically distributed, with mean mu and variance sigma squared. The sample variance s squared is an unbiased estimator of sigma squared over all possible random samples of size n that could have been drawn from this population. That is, the expected value of s squared, the expected value of our sample variance, is equal to our population variance. Now, the higher the sigma squared, the greater the variance, the greater the inter-observer variability. Now, to obtain an interval estimate of sigma squared, a new family of distributions has to be pulled in. And we're going to call this as chi-squared distributions. All right, so here we're going to use the chi-squared distribution whenever we're interested in making estimates on variance. All right, so it works out that if we take the sum of squared values where the values are standard, normally, independent, identically distributed, then this sum of squared values is said to follow a chi-squared distribution with n degrees of freedom. And we're going to call this distribution chi-squared with n degrees of freedom. The chi-squared distribution only takes on positive values and is always skewed to the right. Notice that I've got squaring on there, so it has to be positive or 0. And so, almost surely it's going to be a positive value. and it will be skewed right. And we're making the assumption that our observed data are independent, identically distributed, standard normal. For n greater than or equal to 3, the distribution has a mode greater than 0 and is skewed to the right. The skewness diminishes as n increases. So the larger my sample size, the less skewed the chi-squared distribution is. The youth percentile of a chi-squared distribution with d degrees of freedom is denoted by chi-squared sub d, where the probability that we observe a value less than or equal to this, so there should be a sub u here, is equal to u. So this is the quantile for the chi-squared distribution. Now, interval estimation. To obtain an interval estimate of sigma squared, we need to find the sampling distribution of s squared. We assume that all of our x's are normally distributed with mean mu, standard variance sigma squared. Then it can be shown that s squared is going to be distributed to a chi-squared random variable n minus 1 degrees of freedom times sigma squared divided by n minus 1. You'll notice that mu does not play a role on this. Now, if x is normally distributed with mean mu and variance sigma squared, then the standardization of x gives a new random variable, z. So if I standardize my random variable, so I take x minus its population average divided by its standard deviation, then this z will have mean 0, standard deviation of 1, and we're going to have normally distributed with mean 0 and variance 1. And we'll work out that if I take the sum of squared deviations from the population average, added up, divided by sigma squared, that will in fact be a chi-squared distributed random variable. So we estimate mu by x. However, if we substitute x or x bar for mu, then we lose 1 degree of freedom. So here, the difference in these two boxes, here I'm subtracting by mu, here I'm subtracting by the sample average. Okay, so here I'm taking my data and I'm taking an estimated value. All right, well, instead, this is the true value that I don't actually know. I wish I did know. Here's the true value. I wish I knew it. I don't know it, so I'm going to estimate it. Theoretically, this would be chi-squared with n degrees of freedom. Here, I'm inducing a little bit more variability because now I'm using my data in a second way. And so that invokes more randomness. Because of that randomness, I'm going to have a more spread out distribution, n minus 1 degrees of freedom. All right, so S, our estimate of the population variance, is x minus x bar squared, add up all of the values, divide by n minus 1. All right, multiply both sides by, take this equation, multiply both sides by n minus 1. So we have n minus 1 times s squared is equal to the sum of squared deviations. Now, if I look at this, if I divide both sides by sigma squared, the left-hand side divided by sigma squared, I know that this is going to be a chi-squared n minus 1 degrees of freedom. So I use this fact and I use what I have here to get a confidence interval for what's going on. All right, now let's talk about point estimation of a binomial parameter p. Let x be a normal random variable with parameters n and p. An unbiased estimator of p is given by the sample proportion of events, p hat. So this is the number of times I have success divided by number of trials. Its standard error is given exactly by p times q square root divided by n. So this is p times q divided by n, all of that underneath the square root. The square root captures this entire fraction and is estimated by p hat q hat divided by n square root. A better justification for the use of p hat to estimate the binomial parameter p is that p hat is a maximum likelihood estimator of p. All right, so to understand this concept, we need to define likelihood. The probability mass function of a discrete random variable x is a function of k parameters, p1, p2, p3, all the way to pk, denoted by like p and then this underline thing. If x1, x2, xn all the way up is a sample of n independent observations from x, then the likelihood of the sample x1, x2, x3 up to xn given by the probability mass function denoted by L of x given p and represents the probability of obtaining our sample given specific values of the parameter. Okay, so what's going on here? When I talk about likelihood, I'm turning things around. If I was to have a probability distribution function for a sample, right out of the bat, I'm treating the observed data as like a random variable, and I'm treating the parameters as constant fixed values. In likelihood, what I'm doing is I'm flipping that around. In likelihood, I have the data in my hands, but I don't know the parameters. So what I'm going to do is I'm going to take that same functional form that I have from college algebra, I'm going to plug in my observed data, and I'm going to leave the parameters as the unknown variables. Then I'm going to do some calculus, and then I'm going to find what maximizes that function on those parameters. All right, suppose we have a probability mass function or a probability density function that is a function of k parameters, p1, p2, p3, all the way up to pk. The maximum likelihood estimator, MLE, of the parameters, p1, p2, p3, all the way up to pk, are the values here, this is just note writing it down, which maximize the likelihood. Heuristically, the maximum likelihood estimate can be thought of as the values of the parameters that maximize the probability mass function, given the data. For large values of n, my binomial sample average is approximately normally distributed with mean mu equals p and variance p times q divided by n. And so we can approximate the normal distribution with mean p and p times q divided by n, where here, when I say normal distribution, this is number of observations divided by number of opportunities to be successful. So the number of successes in a binomial trial, and we can tinker around with this and modify this around and change it up so that if I just want the count of successes, I can have normally distributed of n times p for the expected value and n times p times q for the variance. And so we can take this a step further and get a confidence interval on what the probability of success is by using this formula here. And it's the same trick we've been doing over and over and over, point estimate plus or minus normal distribution for the confidence level I want times the standard error. Now, this method of interval estimation should only be used if n times p times q, the estimated values, are greater than or equal to 5. Different textbooks will give different values. 5 is the lowest I've ever seen. All right, now, it is possible with modern machines to go ahead and actually crunch that out. When I was talking about the normal distribution on the last slide, that's only an approximation. Using a computer, we can actually get the exact true values of confidence intervals instead of using an approximation. If you do it that way, I recommend that you do it that way. Just let the machine do the work. Don't do it yourself. You have a computer for a reason. Now here's a table. These tables were more important before computers, before SAS, Stata, SPSS, R, Python were readily available. Here, this just, it's just saying that we can just go through and get these values really easy off of, Excel or whatever we want. Now we also do point estimation of the Poisson distribution. So remember, the Poisson distribution is for counts, and we have one parameter, the expected value. So then this is the number of events over a specified time interval. All right, so let's assume the number of events, X over T person years, is Poisson distributed with parameter mu equal to lambda times T. An unbiased estimator of lambda is given by X divided by T, where X is the observed number of events over the T time span. If mu is the incidence rate per person year, T is equal to the number of person years of follow-ups, and we assume a Poisson distribution for the number of events X over T person years, then the expected value of X is given by lambda times T. Shouldn't be surprising given it's a Poisson distribution. So the expected value of lambda hat is equal to the expected value of X divided by T. T is a constant. So here replace expected value with lambda T, and we just get lambda. So lambda hat is an unbiased estimator of lambda. So here's the exact method for obtaining confidence intervals for a Poisson parameter lambda. And once again, you could go through, you could crunch this out manually. Just let the machine do it. Whatever you're doing, don't do this by hand. Like every statistics platform will figure this out for you. All right, so we can also get one-sided parameter estimates. So there, in that situation, we only care about one side greater than or less than, particularly like we want upper bound or we want lower bound. And here we can fine tune our results to what we want. Maybe I don't want a closed off interval. I only want one end of it. I want to know what is the cutoff on one side. And using the one-sided approach, I can improve my estimate of that one cutoff. All right, so let's recap what we talked about. We talked about sampling distributions. So this is critical for understanding the principles of statistical inference. We talked about minimum variance unbiased estimators of mu, specifically X bar. We talked about maximum likely estimators, MLE of mu. We talked about the central limit theorem. We talked about interval estimation of confidence intervals, and we talked about T and chi-square distributions to obtain interval estimates. That's all I've got for you. Take care and goodbye.